Bismillahirrahmanirrahim. Today, this is the second lecture of Chapter 4, Thermochemistry and Fuels. We have talked about fuel, the combustion temperature, the combustion equations, the chemical equilibrium, and we have talked about the hydrocarbons, how there are different types of hydrocarbons and gasoline. Now, let's see what the fuel has to do with our ignition and with our engine. Self-ignition and octane number. Now, self-ignition characteristic of fuel, we have studied a lot about the fuel and their thermochemistry. Now, if the temperature of an air-fuel mixture is raised high enough, the mixture will self-ignite without the need of the spark plug or other external igniter. The temperature above which this occurs is called the self-ignition temperature. If we compressed the air-fuel mixture in a combustion chamber to such a level that the temperature is risen so high and it self-ignite, then this temperature is known as this thing is known as self-ignition temperature. If the temperature of an air-fuel mixture is raised high enough in the combustion chamber, the mixture will self-ignite without the need of the spark plug. So you do not need a spark plug to ignite that mixture or any external source. It will automatically self-ignite, and this temperature above which this occur is called the self-ignition temperature, SIT. Self-ignition or pre-ignition or auto-ignition. So there are different names we call it. Self-ignition, pre-ignition, or auto-ignition is not desirable in an SI engine. So it is not desirable, it is not required in a spark ignition engine, where a spark plug is used to ignite the air-fuel mixture at the proper time in the cycle. Because your spark plug is timed to ignite at a specific crankshaft rotation to give a spark to ignition to the combustion fuel. The compression ratio of a gasoline-fueled SI engine are limited to about 11:1 to avoid self-ignition. So the compression ratio of an SI engine is always lower as compared to CI engine. In CI engine, we require a high compression. So the range is 11:1. It is because to avoid self-ignition. When self-ignition does occur in an SI engine higher than desirable, the pressure pulses are generated. But when self-ignition does occur in an SI engine higher than desirable, pressure pulses are generated. These high pressure pulses can damage to the engine and quite often are in the audible frequency range. This phenomena is often called knocking or ping. So these undesirable pressure pulses which are generated, these are known as knock or ping. Now, self-ignition characteristics of a fuel. First, let's read this. Cylinder pressure as a function of time in a typical SI engine combustion chamber, showing A, normal combustion, B, combustion with light knock, and combustion with heavy knock. Now let's see figure A. On x-axis we have a time and y-axis we have a pressure. Now your piston is moving from TDC to BDC at specific time. You have a peak pressure here, okay, of air fuel mixture. So there is no self-ignition and there is a smooth combustion. But we are having a cylinder in which we have a light knock. When it reaches a peak pressure, after the peak pressure, cylinder peak pressure, the air fuel mixture, there is some self-ignition. And then self-ignition, these are the pulse waves which are pressure waves which are generated and which are not desirable. It's a slight knock here. Now in the third case, when we have a heavy knock, when we reach the peak pressure and it is quite a huge self-ignition there, and we have pulse generation, pressure pulse generation, and we have a high knock in the cylinder. And these are in audible range, so we can see a different kind of noise from an engine. Now, self-ignition characteristics of a fuel. If the temperature of a fuel is raised above the self-ignition temperature, the fuel will spontaneously ignite after a short ignition delay time. The higher above the self-ignition temperature which the fuel is heated, the shorter will be the ignition delay. Ignition delay is generally on the order of thousandths of a second. Let's see this. We have a time here, this we have a temperature, and this is the self-ignition temperature. Now we have a compression stroke, we have a compressive heating here, and this, when it passes self-ignition temperature, we have a ignition delay, and then we have a combustion. Ignition delay, and then we have a combustion. So this is the ignition delay. Now let's take another example. SI engine combustion chamber, schematically visualized as a hollow long cylinder with a spark plug located at left end. We have converted this cylinder in a long hollow cylinder, combustion chamber, and we have placed a spark plug here. Mass of air fuel is equally distributed as the plug is fired to start combustion. So your piston is moving from VDC to TDC. At the end of the compression stroke, your spark plug gives spark or ignites and start the combustion process. Before that, we have distributed the air fuel mixture uniformly in these four sections. Okay. Now, your spark plug has started firing. Okay. As the flame front moves across the chamber, now spark plug is at this point. Your combustion started and the flame is traveling in this hollow cylinder in this direction. Okay. As the flame front move across the chamber, unburned mixture in the front of the flame is compressed into smaller volume. So here we have combustion. Air fuel mixture is burned, and this is the unburned fuel mixture. So it is the hot gases are compressing this unburned fuel mixture here. Okay. Now in C, flame front continue to compresses the unburned mixture into smaller volume, which increase its temperature and pressure. If compression raises temperature of ends gas above self-ignition temperature, self-ignition and knock can occur. Now, here we have seen we have a combustion, and the hot temperature and hot pressure of the gases are exerting its temperature and pressure on this unburned fuel mixture and compressing it. Now, as the combustion increases, propagation is more pressure and temperature on this unburned fuel. When it reaches the self-ignition temperature, there will be a self-ignition here and knock is occur in this region. So I explain again. We take a hollow cylinder and we divide it into four different chambers. And we suppose that their air fuel mixture is uniformly distributed in these four portions. We have a spark plug here at the end, and it starts igniting the air fuel mixture. Your combustion starts. Now we have a combustion here, high temperature, high pressure gases. They are exerting pressure in this direction on the unburned fuel mixture and compressing it. So here we have air fuel mixture, air fuel mixture, air fuel mixing. This is burned, and this will now burn this portion. And pressure is exerting, temperature is exerting in this direction. Now more area, more temperature, more pressure gases, more force exerting on this compressed air fuel mixture. And when the temperature of this region is reaches above the self-ignition temperature, we have a self-ignition here and knock is occur in this region. Now that was the self-ignition, and there will be some ignition delay, and that will be in thousands of seconds. Now octane number and engine knock. Octane number is usually for your gasoline fuels. Remember this thing. The fuel property that describes how well a fuel will or will not self-ignite is called the octane number or just octane. So the fuel property that describes how well a fuel will or will not self-ignite is called the octane number or just octane. This is a numerical scale generated by comparing the self-ignition characteristic of the fuel to that of standard fuel in a specific test engine at specific operating condition. So this number is not generally given. It is numerically calculated on a specific condition and specific operating condition and specific test bench with specific standard fuels. So then we give this octane rating, okay, octane number. This is a numerical scale generated by comparing the self-ignition characteristic of the fuel to that of standard fuels in a specific test engine at specific operating condition. Now, two standard reference fuels used are isooctane. Two standard reference fuels are, that is isooctane 224 trimethyl pentane, which is given the octane number ON of 100. So we have a fuel, reference fuel, that is isooctane, that is 224 trimethyl pentane, and we give it the octane number is of 100. And N-heptane, which is given the octane number of 0. So we have two reference standard fuels. One is given the number of 100 and other is given the number of 0. One is isooctane and other is N-heptane. The higher the octane number of the fuel, the less likely it will self-ignite. Remember that the higher the octane number of a fuel, there is a less likely chances that it will self-ignite. Engine with lower compression ratio can use fuel with lower octane numbers, but high compression engine must use high octane fuel to avoid self-ignition and knock. So remember this thing, engine with having a lower compression ratio can use fuel with lower octane number, but high compression engine must use high octane fuel to avoid self-ignition and knock. Tests used for rating octane number. How we determine the octane number? Let's see. There are several different tests used for rating octane numbers, each of which will give a slight different octane number value. Octane value. The two most common method of rating gasoline and other automobile SI fuels are the motor method and research method. So the two most commonly used method for rating of a gasoline fuel is motor method and research method. These gives the motor octane number and research octane number. Another less common method in the aviation is the aviation method, which is used for aircraft fuel and gives an aviation octane number. So that is specific to the aviation fuel. The engine used to measure motor octane number and research octane number was developed in 1930s. So more than 94 years ago, almost a century. It is a single cylinder overhead valve engine that operates on a 4-stroke Otto cycle. So that engine is a single cylinder overhead valve. So the valves, inlet valves and exhaust valves are in the overhead, means in the head portion. that operates on a four-stroke Otto cycle. It has a variable compression ratio which can be adjusted from 3 to 30. So its compression ratio can be adjusted from 3 to 30. So this is the variable. Test conditions to measure motor octane number and research octane number are given in table. Now let's see the test condition for octane number measurement. We have for research octane number and motor octane number. The engine speed in RPM is 6,900. Inlet air temperature is 52 degree Celsius or 125 degree Fahrenheit, 149 degree Celsius or 300 degree Fahrenheit. Coolant temperature is 100 degree in both the cases. Oil temperature is 57 degree in both the cases. Ignition timing is 13 degree before TDC, and in motor octane number it is 19 to 26 degree before TDC. So your spark plug will ignite 13 degree before TDC in RON research octane number and 19 to 26 degree in this range before TDC in motor octane number. The spark plug gap we will study in detail when we will study spark plug. What is the spark plug gap? 0.508 mm. Inlet air pressure, the atmospheric one, so 1 atmospheric. Air fuel ratio adjusted for maximum knock. Compression ratio adjusted to get standard knock. So we have these two variables adjusted for maximum knock and adjusted to get standard knock. Let's see. Test procedure to find the octane number of a fuel. The test engine is run at specified condition, which in the last slide, these are the test conditions using the fuel being tested. Okay. Compression ratio is adjusted until a standard level of NOx is experienced. So we take a fuel that is an unknown fuel and we run in a specified condition and its compression ratio is adjusted until we achieve a standard level of NOx is experienced. The test fuel is then replaced with a mixture of two standard fuels. So we have an unknown fuel and we are testing it in a specified condition with this compression ratio is adjusted to get the standard level of NOx. At some point, we receive a standard level of NOx with this compression ratio, which is adjusted. Then this test fuel is replaced with a mixture of two standard fuel. And what are those two standard fuels? These are isooctane and heptane. So the intake system of engine is designed such that the blend of the two standard fuels can be varied to any percent from all isooctane to all N-heptane. So the intake system, which the fuel which we are sending in, is designed in such a way that blends the two standard fuels can be varied to any percentage from all isooctane to all N-heptane. The blend of fuel is varied until the same knock characteristics are observed as with the test fuel. So here we have received the standard level of knock with this compression ratio. So with the variation in the blend of that fuel, we achieve this. We change the composition of these two standard fuels. So we receive the same knock characteristics are observed with the test fuel. The percent of isooctane in the fuel blend is the isooctane number, octane number given to the test fuel. So we are using the mixture, the blend of the fuel, get the same knock characteristics which we have used with that unknown fuel which we have tested. Now the percentage of the isooctane in the fuel blend is the octane number given to the test fuel. For instance, a fuel that has the same knock characteristics as the blend of 87% of isooctane and 13% of N-heptane would have an octane number of 87. So we give that fuel octane rating is 87. The difference between these is called fuel sensitivity. So we have two different methods, research octane method and motor octane method. So the difference in between these two values, which we will get from RON and MON, is known as the fuel sensitivity. Fuel sensitivity is a good measure of how sensitive knock characteristic of a fuel will be to the engine geometry. So fuel sensitivity is a good measure of how sensitive knock characteristic of a fuel will be to a engine geometry. A low fuel sensitivity number will usually mean that knock characteristics of that fuel are insensitive to engine geometry. So if we have a low FS number, that means fuel is insensitive to the engine geometry. The fuel sensitivity generally ranges from 0 to 10 by measuring octane numbers above 100. Now we have a range from 0 to 100, but if we have to measure the octane numbers above 100, so fuel additives are mixed with isooctane and other standard points are established. So in that case, we have to add some additives with the mixture of isooctane and some other standard points are established. Now to obtain the octane number more than 100 or to increase the octane number, a commonly additive used for many years to raise the octane number of a fuel was tetraethyl lead, TEL. So a common additive used for many years to raise the octane number of fuel was tetraethyl lead, TEL. Common octane number anti-knock index for gasoline fuel used in automobile range from 87 to 95, with higher values available for special high performance and racing engines, whereas anti-knock index is equal to RON plus MON divided by 2. Reciprocating SI aircraft engine usually use low lead fuels with octane number in the range of 85 to 100. In several fuels of known octane number are mixed, a good approximation of the mixture octane number is octane number mixed is equal to percentage of A of fuel octane number plus percentage of B octane number plus percentage of C octane number, where percent is equal to percent mass. The factor that increases NOx deposits build up on the combustion chamber walls. So during the combustion, there are a lot of deposits build up on the combustion chamber walls, maybe on the clearance volume reduction, the heat barrier formation, improper ignition timings, improper fuel distribution to cylinder, surface ignition due to surface deposits. So all these factors leads to increase the NOx. Now, critical compression ratio as a function of fuel octane number, anti-NOx index used in an engine. Critical compression ratio is above which many engines could have a NOx problem. So octane number, AKI, and compression ratio. This is the graph. More the compression ratio, more the octane number is anti-NOx index. Octane number increases as a function of TEL added to gasoline varies somewhat with gasoline blend. Octane number is MON, RN, or AKI. So let's see. On our x-axis, we have tetraethyl lead grams per liter. See, you add only 1 grams per liter that TEL and your octane number increases to 11. So this how your tetraethyl lead increases the octane number. Now, example 4-5, a gasoline type fuel is generated by blending 15% by weight of butane 1, 70% trip, tri, trip, triptane, and 15% isodecane. Determine the anti-NOx index, AKI. The anti-NOx index is zero point 0.4 gram of tetraethyl lead is added per liter of fuel if the fuel is sensitive to combustion chamber geometry. Let's see. Using data table A2, equation this, let's find out the research octane number. So we know the compression ratio, we, we know the percentages of these fuels and the molecular weights of these fuel. 0.15 into 99.70 into 112.15113. So the research octane number comes out to be 110.2. For motor octane number, we get 0.1580 plus 0.70 from the table 10, and we get the value of 96.5. So the anti-NOx index, we know that MON plus RON divided by 2. So the anti-NOx index is 103. Now if we use 0.4 gram per liter of, so it will increase octane number to the rating of 7 from this graph. 0.4, it will be 0.7. So 103 plus 7, so anti-NOx index with that is 110. So the fuel sensitivity is fuel sensitivity RON minus MON. So 110.2 minus 96.5. So it gives us 13.7. So which is more than the range 0 to 10. This is fairly a large number, which suggests that NOx characteristics of this fuel are very sensitive to combustion chamber geometry. Now, talk about the diesel fuel. Diesel oil or fuel oil is obtained over a large range of molecular weights and physical properties. Various methods are used to classify it, some using numerical scales and some designating it for various uses. The greater the refining done on a sample of a fuel, the lower is its molecular weight. The lower is its viscosity and greater is its cost. Numerical scales usually range from 1 to 5 or 6, with subcategories using alphabetical letters A1, 2D, etc. The lowest number have the lowest molecular weight and lowest viscosity. The higher numbered fuel are used in residential heating units with industrial furnaces. Fuel with largest number are very viscous and can only be used in large, massive heating units. Each classification has acceptable limits set on various physical properties such as viscosity, flash point, pour point, cetane number, sulfur contents, etc. Light diesel fuel and heavy diesel fuel, two categories of diesel fuel. Light diesel fuel has a molecular weight of about 170 and can be approximated by a chemical formula C12.3H22.2. We can see from the table A2. Light diesel fuel will be less viscous and easier to pump, will generally inject it into smaller droplets and will be more costly because of the molecular weight is less. Heavy diesel fuel has a molecular weight of about 200 and can be approximated as C14.6H24.8. Heavy diesel fuel can generally be used in large engines with or heavier engines with higher injection pressure and heated intake systems. Often an automobile or light truck can use less costly, heavier fuel in summer, but must change to lighter, less viscous fuel in cold weather because of cold starting and fuel line pumping problem. So remember this thing. If you have an automobile or light truck, you can use less costly, heavier fuel in summer, But in winter, we have to switch to the lighter and less viscous fuel because of the cold starting and fuel line pumping problems. Cetane number. In gasoline, we have octane number, but in diesel fuel, we have a cetane number. In compression ignition, CI engines, self-ignition of air-fuel mixture is a necessity. So we don't have a spark plug in diesel engine. We don't have any other ignition mechanism. So you have a compression ignition engine in which we self-ignition of air-fuel mixture is a necessity, is a must. The correct fuel must be chosen which will self-ignite at the precise proper time in the engine cycle. So it is therefore necessary to have a knowledge and control of the ignition delay time of the fuel. So we are using the fuel. We must be knowing about the properties and the characteristics of the fuel and the ignition delay time of that fuel. The property that quantifies this is called the cetane number. The larger the cetane number, the shorter is the ignition delay. So a diesel fuel having a larger the cetane value, its ignition delay will be shorter, and the quicker the fuel will self-ignite in the combustion chamber environment. A low cetane number means the fuel will have longer ignition delay. Now, comparing the test fuel to two standard references fuel, the fuel components N-cetane, hexadecane, C16H34 is given the cetane number value of 100. As we have in gasoline, we have two standard references fuel. So same is the case in diesel fuel. We have N-cetane hexadecane with cetane value of 100 and heptamethyl nonane HMN C12H34 is given a value of 15. So where in gasoline we have N-heptane with zero value, but here heptamethyl nonane we have a cetane value of 15, not zero. The cetane number of other fuel is then obtained by comparing the ignition delay of that fuel to the ignition delay of mixture of blend of the two references fuel. The cetane number of fuel is equal to percent of N-cetane plus 0.15% of heptamethylnonane. So this is how we can find the cetane number of that unknown fuel. Cetane number measurement procedure. A special CI test engine, as we have in gasoline, we have special test engine with special conditions. So in this case also, a special CI test engine is used, which has the capability of having the compression ratio change as it operates. Same as we have in gasoline engine, we can change the compression ratio from 3 to 30. Fuel being rated in is injected into the engine cylinder late in the compression stroke at 13 degree before TDC. So we have a compression stroke and we inject the fuel at 13 degree before TDC. The compression ratio is then varied until the combustion starts at TDC, giving an ignition delay of 13 degree of the engine rotation. Without changing the compression ratio, the test fuel is replaced with blend of two references fuel. Using two fuel tanks and two flow controls, the blend of the fuel is varied until combustion is again obtained at TDC and ignition delay of 13 degree. Normal cetane number range is about 40 to 60. So the cetane range is 40 to 60, whereas in octane, the range was 0 to 100. Octane range was 87 to 95. But in cetane, we have a range 40 to 60. Reason to find now few words regarding the alternate fuels. We have studied the gasoline fuels, we have studied the diesel fuel. Now people are working on alternate fuels, alternate source of energies. So reasons to find the alternate fuels are crude oil and petroleum products will become very scarce and costly to find and produce, emission problems, and foreign trade deficits. So these are the three main reasons to go for alternate fuels. Limitation to use alternate fuels, modified engines which were originally designed for gasoline or diesel fuel. Alternate fuels are very costly at present, lack of distribution points. So these are the limitation in using the alternate fuels. Some alternate fuels are alcohol, methanols, ethanol, hydrogen, and natural gas, methane. The advantage of alcohol as a fuel includes can be obtained from number of sources, both natural and manufactured, is high octane fuel with anti-knock index number of over 100 due to high flame speed. So alcohol fuel have a high octane number and anti-NOx index is above 100. Engine using high octane fuel can run more efficiently by using higher compression ratios. So generally less overall emission when compared with gasoline. When burned, it forms more moles of exhaust, which gives higher pressure and more power in the expansion stroke. Has high evaporative cooling HFG, which results in a cooler intake process and compression stroke. This raises the volumetric efficiency of the engine and reduces the required work input in the compression stroke. Lower sulfur contents in the fuels are there. Few disadvantages while using the alcohol fuels: lower energy content of the fuel, more aldehydes in the exhaust. Alcohols is much more corrosive than gasoline on copper, brass, aluminum, rubber, and many plastics. So this is another disadvantage. Poor cold weather starting characteristics due to low vapor pressure and evaporation. Poor ignition characteristics in general. Alcohol have almost invisible flames. Danger to store tank flammability due to low vapor pressure. Low flame temperatures generates less NOx. Many people find the storage door of alcohol very offensive. Vapor lock in fuel delivery system. So these are the few limitation or disadvantages while using the alcohol fuels. Now another fuel, the hydrogen. The advantages of hydrogen as fuel: low emissions, essentially no carbon monoxide or hydrocarbon in the exhaust as there is no carbon in the fuel. Most exhaust would be H2O and nitrogen. Fuel availability. There are a number of different ways of making hydrogen, including electrolysis of water. Fuel leakage to environment is not a pollutant. High energy contents per volume when stored as liquid. This would give a large vehicle range for a given tank fuel capacity. Disadvantages of a hydrogen fuels: heavy, bulky fuel storage, both in a vehicle and at the service station, difficult to refuel, poor engine volumetric efficiency, fuel cost would be high at present day technology and availability, high NOx emission because of high flame temperature, can detonate. Remember this. Now, alternate fuels, the natural gas, the methane. Natural gas is a mixture of component consisting of mainly methane 60 to 90% with small amount of other hydrocarbon fuels component. In addition, it contains various amount of nitrogen, carbon dioxide, helium, and traces of other gases. It is stored as compressed natural gas (CNG) at a pressure of 16 to 25 megapascals, or as a liquid natural gas (LNG) at a pressure of 70 to 110 pressure of 70 to 210 kilopascal, and a temperature of around minus 160 degrees Celsius. As a fuel, it works best in an engine system with a single throttle body fuel injector. This gives a longer mixing time, which is needed by this fuel. The advantages of natural gases are octane number of 120, which makes it a very good SI engine fuel. One reason for this high octane number is fast flame speed. Engine can operate with high compression ratio, low engine emissions, less aldehydes than with methanol. Fuel is fairly abundant worldwide, with much available in the United States. It can be made from coal, but this would make it more costly. Now, few disadvantages of using natural gas as a fuel. Low energy density resulting in low engine performance. Low energy density resulting in a low engine performance. Low engine volumetric efficiency because it is a gaseous fuel. Need a large pressurized fuel storage tank. Most test vehicles have a large range of only 120 miles. This is some safety concern with pressurized fuel tanks. Inconsistent fuel properties. Refueling is slow process. So this comes the ends of this lecture. So this completed our chapter 4.